Hello everyone, welcome to my workshop Fun with Conditional Types and other advanced type topics. My name is Titian Cernicova-Dragomir, and today we're going to go through some of the interesting features that the TypeScript type system has to offer. We're going to cover a lot of topics. I think that you might already be familiar with some of these, and I hope that I can add some extra information for you. But if you're not familiar with any of them, then don't worry. We're going to take it slowly, we're going to cover the basics before we move on to the more interesting stuff. So without further ado, let's actually start and dive into this workshop. The first idea that I want to discuss is the idea that we can look at types as sets. Now, what do I mean by this? Well, if we were to have an object type with property foo, then this represents the set of all values that can be created that are objects and have this foo property of type number. Similarly, we could have an object type with a bar property, and this also represents the set of all possible values that are objects and have this bar property of type number. Number represents the set of all values that are floating point numbers that can be represented in JavaScript. Similarly, the type string represents the set of all values that are strings. The type never is actually a special set. It is the empty set. This means that there are no values that can inhabit this set. Its counterpart is the type unknown, which also represents a set, but it represents the set of all possible values. If you can create this value in JavaScript, then it belongs to this set, so it has the type unknown. So armed with this new understanding of types, let's see what operations we can perform on types that are similar to set operations. The first one would be unioning. And this is the same concept as set unions. Namely, if we create a new set that represents the union of two other sets, that means that we're creating a set that has values that can either belong in the first set or in the second set. Similarly, if we create the union of two types, what we're creating is a new type whose values can either satisfy the conditions described by the first type or the second type. This means they can either have a foo property of type number or a bar property of type number. So this is the new set that we are describing. Similarly, if we have a union between string and number, this means that we want all values that are either strings or numbers. The second set operation we can perform on types in TypeScript is intersections. So it again is the same concept as the set operation. Namely, if we take the intersection of two other sets, we're left with only the values that belong to both sets simultaneously. So for example, if we create the intersection of our two object types, what we get is a new set, or a new type, which has objects that have both a foo property of type number and a bar property of type number. Similarly, we can create a new intersection between number and string, and this creates the set, or the type, of all values that are simultaneously both string and numbers. And I know what you're thinking right about now. What value is both a string and a number? And the answer is that no value will satisfy this intersection. So what we get is actually the empty set, which reduces to the type never. And we will see this happening in several places where intersections that can never happen will reduce to the never type. So let's see what we can do with unions and intersections. So the first question we're going to look at is how can we represent an object that either is an engineer or a doctor? And the simple answer is that we can use a union. So we have a function, let's call it printPerson, which we want to use to either print a doctor or an engineer. And this is simple enough, and right now we can call this function and we can say printPerson, and we can pass in any object literal. And when I say any object literal, I mean that the type here is any, so we can pass in anything. So this of course means that we don't get completion and we can have all sorts of errors that we don't want to have. So how can we improve the type of printPerson? Well, the answer is simple. We can say that person is either an engineer or it's a doctor. And this seems very simple, and now we get type checking where we actually try to use this union. We have to specify now the name, we have to specify the age, we have to specify the field this person is working in, and that's it if we're just printing a person, an engineer. And if we want to create a doctor, we have to specify the specialty, and this also works fine. Now, inside the function, we can access some of the properties of these. For example, we can access name, and we can access, for example, age. The problem is that we cannot access properties that are not common to both of these two interfaces. Why is that? Well, given our understanding of how a union works, we can only guarantee that these two properties will be on the object that can be passed inside the parameter p. Why? Well, because p can either be a doctor or an engineer. They both have name and age, so definitely that object will have name and age, but we don't know if we are getting a doctor or an engineer, so we cannot access field or speciality. And this moves us to our second question. Why can't I access some properties of the union? We already understood that, and the thing we're going to look at next is how we can access them safely. And the answer is we can narrow the union. Now, there are several ways we can narrow a union, but for this type of union that is not discriminated and is a union of object types, the simplest way we could do this is using the in operator. So for example, we can say that if speciality in P, then we actually get access to the speciality field. And this is called union narrowing. And it's called narrowing because basically we took this type, which is a wider set, and we narrowed it to just one of the union constituents. In this case, if we checked for speciality, we now have P is typed as doctor, because that is the only part of the union that is left. On the other side, we could access the other property of the union that we couldn't access before, namely field. Why is that? Well, TypeScript is smart enough to understand that if on this side we narrow the union and we handle the doctor case, what's left on the else case is only the other part of the union, namely an engineer, and we can access the fields of engineers without any more restrictions. So, we saw how we can narrow a union, namely using type guards. But what are type guards? Basically, they're syntactic constructs that can help us narrow a union. And when I say syntactic, I mean that their form matters. So basically, the form of our code is what lets TypeScript know that this is something that we use to narrow the type of a specific variable. So basically, to narrow the type of a value variable, for this particular case, we used property in value. And this we call this the in type guard. Now, the in type guard can only be used with object unions, right? With unions of several object types. But if we have a union of primitive types, then we can use another TypeScript operator, namely the type of operator, to narrow the type of the union. So for example, we will have to use a construct type of value, where value is a variable that is of the union type, equals some valid JavaScript type. So let's see an example. Here we have a function which has a parameter that is a union of primitive types. Now, we can say if type of P equals, for example, string, then on this branch of the if, P will indeed be a string and we have access to all of its string methods. Similarly, we can do here if type of P equals Boolean, we can then access Boolean functions here, and P is of type Boolean. And if type of P is a number, then we can do number things on this branch. And of course, on the else branch, what will be the type of this union? Well, since we removed string, we removed Boolean, we removed number from the union, the only thing that is left from this type is actually nothing. So we get the never type on this branch. Now I want to point out that type guards in general don't only work on variables or parameters. You can narrow fields. So for example, if P is not the union itself, but is an object type that has a property that is a union, then we can apply the same logic to narrow this field of the parameter. And the same holds true. We're narrowing p.foo, and then on each branch we will get access to the specific methods and members of the type. And of course on the last branch we actually get that p.foo is going to be of type never. Now, one little thing to be aware of here is that when you're narrowing a field, you're only narrowing the field itself. You're not narrowing the whole object. So, in this particular case, we have P. The type of P is not impacted in any way by either of these type guards. So, P still has a field that is string, number, or boolean. Even though that field, when we look at it, is actually of type string as narrowed by the type guard. Now this quirk means that in some cases you might get surprising effects. So for example here p.foo is boolean, but if we actually try to call a function that requires an object with a field that is boolean, this is actually not assignable because the type guard only impacts the field itself. And this is generally true of type guards. Type guards narrow the symbol that they have been applied to. So in this case a field or a variable or a parameter. If we want to narrow the parent object, we have several options. One of them is to use a custom type guard, but the better option would actually be to use a discriminated union. And we will look at discriminated unions a bit later. But first, let's look at another type of type construct, namely a literal type. And let's start with a motivating question. Namely, how can I strictly type the alignment property of an element, for example, which can be one of the following, can either be center, left, or right. And let's move on to some code. And see, here we have a function. We call it with alignment, and just for the sample, we're just going to log out that alignment. And right now we see that this is a string. While this is technically correct, it means that we can pass any number of valid values in here that are not necessarily valid alignments. So for example, I misspelled center, I wrote it central, and I said except left and right, I also use start and end, which might not be supported. Now, let's see how we can make this be typed a little more specific. And let's start out with a very simple observation. Namely, if we actually write a constant and we say here that it has value right, we actually see that TypeScript doesn't infer the type string for this as it would for example, a variable. Right? If we say a variable here, we would see string. It actually infers the type right. What does this mean? Well, in TypeScript, it turns out that any value, any literal value, can also be used as a type. So for example, if I were to declare a variable right, and I will say that this has type right, then the only value I can assign here would be the value right. If I were to try to assign the value left, well, that wouldn't be correct. Now, string literal types by themselves are not very interesting, because what is good having a variable that can only ever have one value? However, they truly come into their own if we pair them with unions. So, if for example we remove here this string type annotation and we say that this parameter can be either the string literal type or it can be the string literal type left, then we start to see that we get errors on values that are not in this union. What we're doing here is basically that a string literal type represents a value, a set with a single value, for example right, and we're unioning this set with another set that also contains a single value, namely left. And we see here that for these two calls, the TypeScript compiler says that this is okay, but for all the others it says that it's an error. And if we want to add one more, we can also say we support center. So to recap, what are literal types? Well, in TypeScript any value can also be a type, and this type represents the set of value that actually contain only one value. the value that originated this type. Example of string literal types. For example, we can have center, right, and these are string literal types, but we can also have number literal types. For example, 0 or 100, or Boolean literal types, which can only be true or false. And we can have the null literal type and the undefined literal type. Now these are most useful when we pair them with unions. So let's see how we can narrow unions of literal types as well. So let's see in this function, if we use an if statement and we say alignment equals, for example, center, then it means that we have narrowed this union of literal types. And on this particular branch, the only thing that is left is the type center. So alignment can only be center. On the else branch, we see that alignment is what's left of the union. String right and left. Now TypeScript is far smart enough to also figure out conditions that are more complex. For example, we can use an or, and we can say here if it's left or center or right, and then the union is narrowed as expected. We can also do something else. We can actually use a switch statement to narrow the union. So for example, if we say switch alignment, then we can have several cases. So for example, we can have in case the variable is center, and we can do something, and we can also have the case in which it is left, and the case in which it is right. And this works out great. Now if we have a default case here, well, what is left? So we are narrowing the union. We took out the case where alignment could be center, we took out the case where alignment could be left, we also took out the case where alignment could be right. So what's left? If we take out center, left and right from our set that contains only these three values, what's left? The answer is nothing. There is nothing left in this set. So what type represents the empty set in TypeScript? The answer is the never type. Now we can also do here a little trick. Namely, we could define a function that asserts that the value is never, which takes a single parameter of type never. So basically we never expect that any value to actually be passed into this function. And we can do something here like, for example, throw a new error. Now, if we were to use this function in our default, this all works as expected, right? There's no compilation error here, because TypeScript will have narrowed alignment down to never, and we're calling assert never with a value that is never. But if, for example, we were to add here other cases, for example, start, then we get an error, because now alignment is no longer never, it's no longer the empty set, it's the value start. It has a type that can be something. So we cannot assign what is the empty set to, we cannot assign this new string literal type to the empty set. This is not something that is possible. So now we get an error when we add new items to our string literal type union. And this ensures that all of the cases are dealt with as expected, and we never fall to the default branch, which is an error branch in this case. So, as we saw, we can use the equality operator or the not equality operator to narrow unions, and we can also use logical operators, and they will work just as we expect them in type guards. We can also use switch statements to narrow unions, and we also saw a little trick how we can ensure that our switches are exhaustive. Now, I want to talk a little bit about strict null checking, which is something that everybody might be familiar with already, but let's look at it with our new understanding of types. And namely, what does strict null checking do? What does this flag do in TypeScript? Well, what it does is really simple actually. It just carves out null and undefined out of other types. So in terms of sets, the values null and undefined are not part of the sets described by a type anymore. Now, when I said previously that number is the set of all floating point numbers, What I meant was, if we don't have strict null checking on, is that it is the set of all possible numbers and the values null or undefined. Similarly, string is the set of all string values, or null or undefined. Now, if we add strict null checkings, if we enable this flag, the number just becomes the set of all floating point numbers without null or undefined, and similarly for string. And if we want to allow null or undefined, we can actually union these the base types with null or undefined to allow in those values back into the sets represented by those types. So let's see how this works in practice. Well, if we were to take our previous example, we could say that alignment is left, right, center, start, or we can also add undefined as a possible case. Now we see here that our assertion now fails because this is not any more never. Basically, on our default branch, we were left with the value undefined. So how do we get rid of this? Well, again, we can use an if. And the simplest way to take out undefined is to use the not operator on our variable. Now, if not alignment is true, the only value that alignment could be here is undefined. And similarly, if we were to add back null as well. Now, if we were to reverse this condition, if alignment, what we will be doing is basically eliminating undefined and null from the set of values that alignment can be. So what we're left with is just the string literal types that we saw before. So we can say if not alignment, then we do an early return. And now we get back to a case where we have dealt with all the possible conditions, all the possible values that alignment could have. Now let's continue looking at an interesting case. So if we have two types and we put them in a union, we see that something strange happens. If we take the same object literal and we try to assign it to doctor, it fails. If we assign it to engineer, it also fails. But it actually succeeds when we try to assign it to the union doctor or engineer. So what's happening here? We see that the object literal we're trying to assign has the properties name, specialty, and field, while doctor only allows name and specialty, and engineer only allows name and field. By default, TypeScript will actually do what is called access property checks if we try to assign a new object literal to a reference of a specific type. So in the first case, it fails because it does this access property checks and it sees that field is extra and it shouldn't be there. In the second case, we see that it fails because our object literal has specialty and engineer doesn't have this field, so that is also a reason for access property checks to trigger an error. But in the third case, we see that if we try to assign the object literal to something that is a doctor or a person, it actually can allow any of the fields that are present in any of the constituents of the union. So this is by design, and the simple way to get around this is to use a discriminated union. We will see another solution for this a bit later on, when we actually don't change the structure of the types, but we manage to create a condition where these extra fields are actually an error. But for now, let's see what a discriminated union is and how we could use it to get around this issue. So, I just want to point out that unions only allow fields that are present in at least one constituent. So you can't specify any field, and the type of it will actually be checked. So you can't have, for example, a field that is a number when the field should be a string. But the fact that it does allow extra fields is something that might not be always in our best interest. So how can we deal with this? Well, the simple answer is to use a discriminated union. And what is a discriminated union? A discriminated union is a union that has a field that is of a literal type that is incompatible between different constituents of the union. So for example, here we could add a type field which is going to be of the string literal type D, and here we have another type field that is going to be the type E, the string literal type E. So now when we create our doctor, we can specify that it's definitely a doctor. The TypeScript compiler doesn't have to guess which one of the union constituents we're trying to initialize. And here we can say it's a type E, type engineer. So now if we try to assign one of these object literals to our union, we see that we either get an error on the field, or we get an error on speciality. Okay, great. Now, let's see something else about these unions. Let's see how we can narrow a discriminated union. So remember when I said that type guards don't narrow the type of the parent object, they only narrow the type of a field if they're applied to a field? Well, this is true, but discriminated unions are actually an exception to this rule. So for example, if we narrow p.type equals D, well then we've actually narrowed P itself to just be a doctor now. It's no longer a doctor or an engineer, and we have access to all the fields. And if we have a function that only takes a doctor, well, we can actually pass the parameter as a doctor. So if we have a discriminated union, the type narrowing actually does narrow the whole object itself. It doesn't narrow just the field. And this is a very important distinction. So when do we create a discriminated union? Well, a discriminated union has to have a discriminant property, which has to be either a union of literal types or is a union that contains at least one literal type. And when we narrow the discriminant field, we actually narrow the whole object that that field belongs to. So we saw a couple of type guards that we can use for variables. What about unions? What about discriminated unions? Well, we have similar type guards. We can use the equals and the not equals and all of the other type guards in if statements. We can use a switch type guard. So for example, here we could have used a switch and it will work. We can have a case where we have doctor, and then on this branch we will actually have a doctor. And we can have another one where we say we have type engineer, and we can access the field of that engineer. And on the default branch, well, we're going to have P be typed as never, because again we're excluding each constituent of the union in turn. And then on the default branch, there's nothing left in this in the set described by this type. So if we took out all the doctors, we took out all the engineers from our set, then there should be nothing left in this set. And the same trick of asserting never to ensure that unions are exhaustively checked also works for discriminated unions. Now, before we move on from discriminated unions, I'd like to point out some examples that aren't actually discriminated unions. So, for example, here we have these three types, and the union here is actually a discriminated union because the field type is present across all union constituents and is of a literal type in each one of these constituents. But let's see what happens if we actually change type here to be a number and here to be a boolean. Now we can still discriminate doctor. We can still take out doctor from the union using a simple equals type guard. So we can say p.type equals D, and this still works. And here inside, if we call with doctor, we can see that P is actually a doctor type. We haven't had just the type of field narrowed down. Now, what are we left on the else side? Well, on the else side, we have an engineer and an artist, or an artist. So, can we discriminate these two members of a union? Can we have on one branch only the engineers and on the other branch only the artists? Well, we could use a type of type guard and say p.type equals number. Now, an expectation would be that here we would get only the engineers, because the field type is number only in engineers. But TypeScript actually doesn't narrow P here to just engineers, because this is no longer a discriminated union, right? Neither of the types of the type field is a literal type, so we cannot narrow the whole object. So what we're left here is, on the if side, we have P is still an engineer or an artist. The field was narrowed, so if we access P.type, this is a number, but the whole object was not narrowed. And this is an important distinction to keep in mind, because discriminated unions need a property of a literal type in order to narrow the type of the whole variable instead of narrowing just fields. Let's move on to another topic. Let's see how we could do the following. Let's say we have a union, and it has some string literal members and some number literal members. How can we get only the string or only the number constituents? And we're going to look at another option to do this a bit later using conditional types. But right now, let's just use what we already know. We've heard about unions and we've heard about intersections. And let's see how we could use an intersection to actually do this, to just get the string constituents or the number constituents. So let's see, if we were to create a new type, and let's say we just want the string constituents. How could we do this? Well, if we take loose boolean and we intersect it with string, if we hover over string values, we see that you only get yes or no. Similarly, if we hover over a new intersection that contains number instead of string, we can see that we only get the number values. But let's dive a little bit into how this works and more explicitly why it works. Now, one thing we need to keep in mind about unions and intersections is that when TypeScript sees a type that looks something like this, it will try to apply some rules to it. The first rule that it will try to apply is to move the intersection inside. So basically what will happen here is that TypeScript will apply the distributive property of intersections and unions. So basically it can just move in that intersection with string inside of the parentheses and distribute it across each constituent of the union. So basically this is the first step that happens, right? Intersection with string goes on the inside. Now, some of these intersections are uninhabitable by any values, so there are no possible values that could be there. So for example, 0 and string, there's no value that can be both 0 and a string, and there can be no value that is at the same time the value 1 and a string. So these reduce to never. Okay, great. So now we already have a simpler type. But what happens next? Well, we get subtype reduction. Basically, if we have an intersection between a literal type and its parent type, well, the parent type just goes away, because if something has to be yes and has to be a string, well, the only string value that can be that value is the string yes. This works in general. If you have D, which is a subset of P, then D and P will just result to D. If we think about it in terms of sets, this also works. So now we have a simpler type yet. We have yes, no, never, and never. We have this union. But unioning with the empty set, well, that's always going to be a null operation. It doesn't matter. So never is just removed from a new union, and we get the final union, yes and no. And the same logic applies if we intersect with string. So this is why when we intersect with string or we intersect with number, this reduction happens, and we actually get we actually can filter out just the string members or just the number members. So we saw that this trick of intersecting with another type to filter out a constituent of the union works with literal types. Could it work with something more complicated? For example, could it work with a discriminated union? And the answer is yes. We can actually go from the person union which is a discriminated union, to just the doctor type without having to rewrite the person union. And let's see how this could happen. So here we have our person union, which has both constituents for engineer and for doctor, and we would like to create a new type, let's call it doctor, that only contains this constituent, the constituent with type D. So how would we go about doing that? Well, we could take the person type and we could intersect it with a new type that has a type property that is the string literal type D. Now, on a set level, right, if we just think of types as sets again, what would be the result of this? So we have a union between something that has a type property that is the string literal type E, that's one set of objects, and we have another set of objects that has a property type that is the literal type D. Well, if we take the intersection of these, well, it's clear that there are no objects in this set that are also part of this set. So this basically can be removed. Now, following the rules for reducing unions and intersections that we previously saw, what actually happens here? So let's just take the type and inline it here, and let's see how union reduction would happen in this case. Union and intersection reduction would happen. Well, like I said, the first step TypeScript does is to actually take this intersection and move it inside. So it will distribute over all the union constituents. Okay, but let's see what happens on this side. If we were to intersect these two types, the type of the property type would actually be never, because there is no possible value that can at the same time be E and D. So what TypeScript does, it actually reduces this to just this simple object type. But since this object type has this never in it, again, it's clear to TypeScript that this is actually not instantiable. There is no value that could satisfy this type. So again, this reduces to never. And now, based on the same rules we saw, namely that never being the empty set inside the union has no effect, this is also removed. And this is why we end up with the type that we previously saw with this intersection, because on this other side there are no simplifications TypeScript will do. It could probably simplify this intersection because it's already contained within the object type, but that doesn't currently happen. So what did you learn from this? Well, we learned that if we have two object types that have incompatible properties and we intersect them, this means that some of the properties will have type never. And if some of the properties have type never, the whole object type may be simplified to never. And we can use this to our advantage when trying to extract certain constituents of unions. Let's look at another interesting question. Let's say we have a function that takes a string parameter. But the string parameter, while it can be any string, there are certain preferred strings. While we can pass in any hex value, right, we can pass it any string, we would like to suggest red and blue for various reasons. We could of course add more colors, but it would be helpful to have a set of values that are suggested to the user when they try to call this function. Now, a naive answer might be, let's use string or red or blue. And let's see what happens when we actually try to do this. So, we have our print color function. It has a parameter that is string, red or blue. And when we try to call this function, well, the parameter appears as only string. And when we try to use code completion, there are no suggested values. Why is this? Well, the answer has to do with how unions and intersection are reduced in TypeScript. So if we have string or red or blue, this has a type of subtype reduction also applied to it. So if D is a subset of P, then if we take the union of these two sets, P union with D, well, the result is just simply P, right? Because we have this parent set, it contains all the values that D also contains. So the result is just P. Similarly, if we have the union string or red or blue, well, red or blue are superfluous. They don't add anything. because string already contains the values red and blue. So there's no reason to specify those separately. So this just reduces to string, and we can see that in the IntelliSense. So what would be the solution here? Well, the answer is we need a way to prevent TypeScript from reducing this union to just string without actually changing the meaning of what is present here. And the way to do this is actually quite simple, is we actually take string and we intersect it with the empty object type. Now this doesn't actually add a lot of information to string. It doesn't change it in any significant way. Any string will still be compatible with string and empty object. But it does prevent subtype reduction. TypeScript will not see that these string literal types are actually contained within the set described by this type. And the pleasant side effect of this is that we actually do get code completion now where we actually wanted it to be. We can pass it any string, but if we invoke code completion, we get a list of specific values that we can pass into this function. Let's look at another application of intersections. So the question here is, how can we create a string that represents a file path in such a way that it's not easy to pass in any string to that type? Basically what we want to do is we want to take something that is usually represented as a primitive type, string or number, and we want to ensure that it's hard to create a string literal or a number literal that is compatible with this new type. The reason for this is simple. We want to make sure that whoever actually passes in a path to our copy function has obtained that path either from a trusted source, or they have checked the fact that that string is actually a path. So let's see how we can do this. So the way we can do this is we need to find a way to ensure that string literals, which are of type string, are not compatible with our path type. How can we do that? Well, the answer is simple. Since TypeScript is a structurally typed language, it will compare the properties of individual values to make sure that they are compatible. So if the string literal is missing a property that our path type requires, then we can ensure this incompatibility. The question is how to do that. And the simplest way to do it is to actually intersect string with an object type that has a property. This property will not actually be there at runtime. It doesn't have to be. It's just there for the type checker, so we can keep track of what is a path and what isn't a path. So let's call this property underscore underscore brand. And at first, let's just type it as any, and we will see something better to use here in a little while, but for now this works. And we can see now that, for example, our source variable is no longer assignable to our copy function, because the type string does not have this underscore underscore brand property. I said we want to ensure that people check before they assume that a string is actually a path. So how can we do this? Well, the simple answer is we can use a function, let's call it isPath, that accepts a string and returns a boolean. Now inside this function you can perform whatever types of checks you want, and you can say that it will return true if the string p is indeed a path. Now if we want to use this new function, we can say if path, if source is a path, then we perform this copy. But we still have a problem. Even though inside our isPath function we performed all the necessary checks, TypeScript is not aware that this has influenced the type of p. Now, we could use a type assertion here, and we can say source as path, and this works. And we could apply the same treatment to destination. But type assertions are by definition not 100% safe, because as we see here, we only checked source. We didn't actually check destination either. It would be great if there would be an automatic way for the type information to flow from isPath to the true branch of the if statement. And the answer is there is such a way. They're called custom type guards. And instead of using Boolean as the return type, we can use a specialized syntax that will let TypeScript know that this function changes the type of P. So we can say here P is path. If isPath returns true, basically the runtime return type of this function is not influenced in any way. isPath returns a Boolean. This specialized syntax will let TypeScript know that isPath is a custom type guard, namely that it impacts the type of its parameter P. So what can we do now? Well, since isPath is a custom type guard, we can remove the type assertion from source. If we remove it from path, that is still an error because we didn't actually check destination. Complementary to custom type guards, there are also custom assertions. Namely that we can say that we have a function, we can say that it's called assert path. It also takes a string parameter, and if our parameter is not a path, then we throw an error. And if we use this function, we know that after this function is called, destination is always a path. Now, the TypeScript compiler doesn't know this yet, but there is a way to let it know. Namely, we can add a type annotation here, and we can say asserts P is path. And now we have a way to assert that a string is actually a path and throw a runtime error if it's not. So these are the two ways we can check strings, either by actually performing a check and using it in a conditional, or by asserting it is a path and throwing an error if it is not. Now, remember when I said the type of this property doesn't really matter? Well, it doesn't matter for compatibility between string and our branded type. And it doesn't matter for compatibility between two paths. It does, however, matter if we actually define another type, let's call it globally unique identifier, GUID. Now, if this new type has the same property and it's of the same type, well, basically these two types describe the same kind of object, right? They describe the same set. They're strings that also have this __ brand property. So these two sets are basically the same set. They're the same type essentially. So this means that if, for example, we were to replace here that source is actually a GUID, well, no error will occur because both of these, path and GUID, are actually the same type. So our isPath check will produce a valid path, which is assignable to a GUID. So how can we avoid this? Well, the answer is to be more specific here, and instead of any, to use a more specific type, preferably a descriptive one. So what we could do here is we could replace any with the string literal type path, and we could replace GUID with the string literal type GUID. And now we actually have this incompatibility between GUID and path. Because the types are different on the brand property, they're no longer compatible between each other. And this is basically what we wanted. Now there is another solution to this. You could also use a unique symbol. I'm not going to show this because you can Google it. It's not that difficult to change. The benefit of that is that you have a stronger guarantee that nobody else will use the same string as you. Unique symbols can be defined in TypeScript code, and TypeScript will ensure that no other symbol is compatible with that particular unique symbol except the one that you declared it at that specific code location. So, just a short recap. What are branded types? Well, basically they're a primitive type that we intersect with an object type in order to ensure that the primitive literals are not directly compatible with this new branded type. This can be done either using a string literal property. It can also be done using a unique symbol as the type for that property. It can also be done using any, but that exposes you to easy aliasing by other types. What are some other applications? Well, we can, for example, create numbers that are guaranteed to be database IDs, or we can create strings that are guaranteed to be GUIDs, like we saw in our example. There are plenty of applications where you could use this, but it's something that you should keep in mind and you should keep in your tool belt whenever you think you have a primitive type that also has an extra meaning. So let's move away from branded types and unions and intersections for a while, and let's look at something else. Let's see, if we have an object type, how can we get a new type that represents all of the keys of that original type? So for example, if we have the person type, we want to get a union of all possible keys. For example, we want to get the name key and the age key, and we want to be able to use this as a separate type. And the answer here is pretty simple. We have our person type defined. This can be either a type alias or an interface, it doesn't really matter. And we can use the key of operator. And we can say key of person. And this will automatically give us a new type that only contains name and age, the two string literal types. So for example, if we want to define here a new variable of type person key, we see that the only two values assignable are the string age and the string name, because person keys only contains these two string literal types. Okay, let's see another type operator, namely the type of operator. Now, what does this help us do? So the motivating question here is, okay, let's say we have defined a variable, we assigned an object literal to it, and we let the TypeScript compiler infer exactly what the type of that variable is going to be. Now the question is, how can we get the type of this variable? We want to get the type of the end variable and then use it for something else without having to rewrite the type again. And the answer is we can use the type of operator to achieve this. So here if we say type, we're creating a new type alias, and we say this is equal to type of end. And if we hover over this, we see that it gives us exactly the type we wanted. It gives us a type with the same properties as env, as the variable env, and with the appropriate types for each property. Now, I want to stress that key of will always act on a type, right? So we say key of person, and here person has to be a type. It can be a type alias, it can be an interface, it can be a tuple type, it can be any type, or any type expression, but it has to be a type. The type of operator, in contrast, acts on variables. So you have to pass it here a variable that is in scope, for example the env variable in this case. Now I also want to stress that this type of operator, although it shares its name with the JavaScript type of operator, it is different from it. Now the JavaScript type of operator will return a string that represents the runtime type of the variable. For example, it could return string or object or whatever else. However, the type of operator will return, as we saw, the type of whatever variable is given to it, the TypeScript type of that variable. So that is very different, and we can differentiate between the two given the context in which they're used. If we have the type of operator that's used in an expression, in a value that will appear at runtime and will be evaluated at runtime, that means that's the JavaScript version. So if we say, for example, if type of env equals object, the type of operator we've used here is actually the JavaScript version of this type of operator. While if we use type of inside a type or a type annotation, that means we're using the TypeScript type of operator, which gives us the full TypeScript type of any variable. Let's look at another question. If we already have a type, let's call it books, how can we get the type that represents a union of all property types inside of that original type? So for example, we would like to define a type, let's call it value of, and we would like this type to return, if we pass in books, we would like it to return string or number, because those are the only types that are possible for keys of the type book. Before we can answer this though, let's look at a simpler question. Let's see how we can just get the type of a specific property. Let's say we want to get the type of pages from books. How could we go about doing that? And the answer is we can use what is called an index type. So we can create a new type. Let's call it type of pages. And we're going to say that it is equal to book. And we can use the indexing operator and pass in here any valid string literal type that can index book. So for example, we could pass in pages. And now we can see that our new type is the type number, same as the pages type. If we change this to big int, then our new type would also be big int, because we're not writing out number, we're referencing the type that is defined inside books for pages. Okay, so now we've seen how we can use an index type. So what does it look like? Well, it has the form T of K, where T can be any type expression. It can be book, it can be type of env, it can be basically any type or type expression that you can write in TypeScript. K, it has to be a valid type expression that can index T. So for example, for book, that would be the string literal type name, or for arrays it could be number. Now, one interesting property of the indexing operation is that it distributes over K if K is a union. So what does this mean? If we have an indexing operation that is indexing with a union, so for example we have T of K1 or K2 or K ... Kn, well, this actually becomes T of K1, T of K2, ... T of Kn. So what practical applications are there to this? Well, it actually comes as the answer to our original question. How can we get all the values inside this type? And the answer is we can use an indexing operation that indexes over all the properties of book. So for example, we can pass in here pages, and we can pass in font size, and we can pass in name, and we can pass in author. Now, that was pretty tedious to type, not to mention the fact that in the future, if this changes, we're all out of luck and nobody will add the new properties to our union. What can we use that we already learned to actually get this union without having to type it out? Well, the answer is simple. We can use key of book, which will automatically give us a union of all keys of the book type. So now we have our new type that represents string or number or big int, which are the properties, which are the types of the properties from our original type. Now we can make this generic if we want. Let's say we can call it values of, and instead of using book, we use a generic type parameter. You can think of these as parameters to types. They're the same as parameter to functions. They will be replaced with whatever we're passing in. So if we say value of t, then we index t with whatever the keys of t are. And now if we want the type of books, the values of books, we can say value of book, and we get them just as we did before. Now there is value in defining this value of type, even though the definition is pretty small. If t is actually a more complicated type expression, it might be difficult to have to write it twice, both in the index and the type that is being indexed and in the key of expression. But I generally use this simpler version if we're just talking about indexing a named type. So I don't usually bother with defining this alias, but that's definitely your choice and you can define it in your team. Let's tie all of these operators together and see how we can use them in a more complicated example. Let's see how we can create a function that safely gets the values from a specific constant. So for example, we could create our constant, let's call it environment. It would have a server property and a port property, and we want to create a function that accepts one of these keys, either server or port, and returns the specific value. Now the reasons for doing this could be multiple. We could want to provide some defaults, or we want to make sure that we can manipulate those values before we actually give them to whoever is using them. But we want to be able to do this in a safe way. So when we pass in server, ideally we want to get back string, and when we pass in port, ideally we want to get back a number. So let's move on to code. Here we have our safeGetter function in its first form. It's actually not very safe. Here we see first of all it allows in any string, even a string that has been misspelled, which is a problem. And we also see that it returns any, so all of our results are typed as any, and this is definitely not what we want. So how can we improve this? The first improvement we can make to this function is to take into account that here s can't be any string. It must obligatorily be a key of this env constant. So how can we get the keys of the env constant? Well, that's simple. We can use key of, type of, env. Remember when I said that key of accepts any valid type expression? Well, we can say key of type of env. We're just building one on top of the other, one operator on top of the other. And what about the return type? Well, any, again, is definitely not the right type here. What we actually want to say is that, okay, maybe a better approximation of this would be any possible value that appears inside this env variable. So we can say type of env, key of type of env. So is this better? Well, the first error appears here, right? We get an error for the misspelled variable, which is great. It's exactly what we wanted. Now, server and port are no longer any, which is great. They're already string or number, which is definitely a narrower type, so it's better. But it's still not great. This will create a lot of developer friction because people will have to do some sort of type guarding to get their strings or their numbers when they know that the alternate of that type guard can never actually happen. So how can we improve this further still? Well, for that we need to make a couple of changes to our get function. But before that, let's do a bit of housekeeping. First, while we can use type of directly, it's a bit tedious to keep typing it out. So I'm just going to create a type alias to put that type into it, to put the type of the environment constant into it. And this will simplify a bit of what we have to write. So here we can change it to key of env, and we can use here this new type alias as well. So how can we improve this? Well, we need to add what is called a generic type parameter to our function. So, generic type parameters are added using the angular brackets right after the function name. And we can say that we are adding a type parameter k. And this type parameter k will be used as the type for the s variable. Now, why did I do this? Well, usually the types of parameters are defined at the moment when you define your function, and that is their final type. With generic functions, we can actually defer the decision as to exactly what type a parameter will have until that function gets invoked, until its call site. So for example, here we can see that for getValue, the type k was inferred as string. Why? Because when we called getValue, we passed in a string here. So that's what TypeScript decided to pass in. Now, we could, for example, also call getValue with a number. That will also work. And then k will be a number. But we don't want to accept any k here, right? We want to be more specific than that, because we already had a better version of this that errored on this misspelled word. We want to say that k must be one of the strings of our environment constant. To do that, we can add here a clause that says k must extend key of environment. So what this means is that k must be one of the following: server or port. What happens now? Well, we see something interesting here. So this one is an error again, which is great because that's what we wanted. But now we see that k is no longer inferred to string when we pass in a string, because it can't be any string. It has to be either server or port. So TypeScript will actually infer for k the string literal type server, which is what we passed in as an argument. For port, it will infer k as port. So great. Now at call side, we have for k a very specific type. We have either server or port, and that is the type of k for that particular call site. Now what can we do with k here? Well, we can index, like I said, with any valid type expression that can be used as an index to env. Okay, well, we can index with k, can't we? I mean, k must be a subtype of key of env, so it can either be the union server or port, or it can be server or it can be port. It can't be anything else. So definitely k can be used to index env. So we can switch here our indexing expression to be env of k. So let's see what happens now. Well, since at this call site k was server, env of server evaluated a string. At the other call site, since k was port, env of port evaluated to number. So now we've managed to satisfy all of the constraints that we placed on this function. Namely, we wanted it to error out on mistaken properties, and we wanted to get the correct type for each property in our original constant. So I think that we managed to do quite a good job here, and I am pretty happy with the results. Hope you guys are too. So let's shift gears a little bit, and let's look at some types that are defined in the TypeScript standard library. And all of these are going to be map types, and we're going to see exactly what that means in a second. But first, let's take them at face value and see exactly what they do. Now, we're going to create a class. We're going to call it form data, and it's going to abstract holding the data for a form. And we're going to track validity, and we're going to have methods that get data. We're going to have methods that get some of the data, and also allow us to set the data in this form. Now, this is obviously a toy example, but it's going to demonstrate some of the behaviors that are useful and can be solved by mapped types. So first, let's understand exactly how this class works. So we have a type, for example, person, and we're creating a new form data of that person. So this is the form that is going to hold data for person, and we initialize it with some data. So the first method we're going to look at is this setSum method, which currently takes a parameter that is of type t. So for example here, setSum would actually have to take a person. But what setSum actually wants to do is to allow us to set some of the fields of person. We definitely don't want to have to specify all of the fields that are required in person. We don't want to have to specify name if we only want to set, for example, age and maybe, for example, company. Now, what we actually need here is a new type, let's call it SumPerson, where all of these properties are optional. Now, we could do something like this. We could spell out this type, and we could also pass it as a type parameter, and for example say here that, okay, you must manually specify a new an extra type, and we'll call it tPartial, and take this new type and use it as the parameter for some fields. And this would actually work, but the problem is that it is very tedious to write this new type, and it's very error prone. We could misspell some of the names, or we could forget to add them when we modify person. So how does TypeScript solve this? Well, it allows us to use a predefined type called partial. And what partial does is it creates a new type with the same properties, but with all properties being marked as optional. So what we can do here, instead of spelling out this type, we can say partial of person. So now if we hover over some person, we see that all of the properties are now optional. Name is optional, age is optional, and also company is optional, which was optional before as well. So now we actually have this type created for us. But this also means that we don't actually need to specify this type parameter inside form data. We can actually just use partial on our type parameter. So we avoid having this need to specify more type parameters than is necessary. So now we have our setSum method correctly typed, in the sense that it will take an object that will contain some of the fields of our original person type. And we get all of the type checking. For example, we cannot misspell a name, and the types of the fields must be of the same type as in our original person type. Moving on, we see here the getValidity method and the isValidByField field, and we see here that these are typed as any. And the question is, what exactly would be a good type here? Well, the type that would be returned here should have all the keys inside of T, but they should be typed as Boolean. So the field is valid or invalid. So what would this type look like? Well, it would be a type, let's call it valid person, and it would basically have all the same fields as our person type, except all of the types would be changed to Boolean. And actually we don't want company to be partial. We would want all of them to be present, because the state of validity should always be there. So how can we do this? Well, the answer is that TypeScript offers another predefined type called record. And what record does is that it takes a union of keys and a type, and it creates a new type with all of those keys, and the type of the keys is going to be the type that was passed as the second parameter. So we can have record of name and Boolean, and this is going to create a new type that is going to contain this single field. Now if we want to create more than one field, we can just pass in a union, and we can say we want here age as well, and we also want company. And now we have the exact type that we want, right? We have a type that contains name, which is Boolean, age, which is also Boolean, and company, which is also Boolean. Now the last change we should make is that we don't want to have to spell out all of the fields. And in this case, since we're just trying to have the same keys as another type, we could just use our key of operator on person, and we are going to get the same type that contains all of the fields, only they're marked as only their type is Boolean. We can also use this type on our type parameter. So we can say that we want a record that will contain all of the keys that are present in T, only they're all typed as Boolean. And we're going to use this as the return type for our getValidity function as well. Okay, so now our getValidity type function is typed correctly, and we see here that we have an error because we were trying to access a field that wasn't there, and we can see that the new return type of getValidity actually has only the fields that we are interested in, and we know that actually exist on our return value. So this was the second map type we saw, record. It creates a type with a given set of properties, all of the same type. Now the third type we're going to look at is read-only, and this creates a type with the same structure as a given type, but with all the properties marked as read-only. So if we were to take our getData method, we want this to actually return the same type, t, but we want all of the properties marked as read-only. So for example, this assignment here should not be possible. So like I said, if we were to take our read-only type, it functions very similar to partial, namely we can just say read-only of person, and this is going to create a read-only person, and if we hover over this type we will see that it has the same structure as person, only with the read-only modifier added. We can use this of course on the type parameter, and we're going to say that getData returns a read-only version of the data, and then when this assignment is attempted, it will actually raise an error when at compile time. The fourth map type we're going to look at is required, which again creates a type with the same structure as the original type, but with all properties marked as required. So for example, here when we have our setAll method, we want to be forced to provide values for all of the fields, including those that are optional in the base type, for example, in person. And again, it functions quite similar to the other ones, to partial and to read-only. And we see here that if we apply it to our person type, we get a type that has the same structure, only company here is not marked as optional anymore, it is required. And if we are to use this on our type parameter, again, when we try to call the setAll method, we are forced to specify company as well. Now, the last map type we're going to look at is pick. And what pick does, it actually picks a set of properties from a given type. And let's take a look at using it simply in types. And let's say that we want to pick from person name. So we have pick. The first type parameter is the type we're picking from. And then we can specify a field. So for example, in this case, P is going to be an object type that only contains name. Now if we want to pick more fields, we can just add them in a union. So we can say we pick name and age, for example. Or name and company. Now what's interesting to note is that pick will preserve the shape and the structure of the original type. So for example, if the original type had a field that was optional, it will be optional in the pick result. If the field was also, for example, marked as read-only, then P is also going to keep this read-only modifier. So it is structure preserving. Now how can we use this pick type in our form data class? Well, we have this getSum method that is going to take it's going to take an array of keys, and it's going to create a new object that contains only those keys. And we would like to be able to use this method by specifying some keys. For example, we would like to specify age and company, but not name. And we would like O to contain only those fields. Now right now O is typed as T, which means it will falsely claim that it returns also the name, when that property is actually never present on the result. So how can we do? Well, we're going to need to use pick to pick out only the fields that were passed in. But similarly to how our example of a saveGetter function needed to know exactly at call site what fields were passed in, similarly this getSum method also needs to know at call site what actual fields were passed in. So we're going to again use a type parameter k, which we're going to say it extends key of t. So k must be one of the keys of t. And this type parameter is going to be used as the type for keys. So we're going to be passing an array of whatever this k type is. So now when getSum is called here, k is going to be inferred to whatever fields we actually passed in to the array. In this case, it's going to contain age and company. So now that we have this information at call site, and for example, and if we were to pass in different fields, k would be different. For example, here we have k is going to be name and age. We can use pick in conjunction with k. So we can say we're picking from t whatever fields were specified in the k type parameter. So for the first call, since k is age and company, we're going to get a return type that is pick of person and age or company. So this means that this type, so this means that O is going to have the age property, it's going to have the company property, but it's not going to have the name property. And similarly, O2 is going to have the name and age property, but not the company property. So I've kept referring to these types as mapped types. But what exactly does that mean? What makes them mapped types? Well, if we go to definition on one of these types, we can see how they look inside the standard TypeScript library. Now you'll see that they share a syntax that we're going to delve in just a little bit later. But first, let's look at a motivating example. Let's see something that we could not solve just using these predefined map types. And the question that I pose to you is very simple. Let's say we have an existing type that contains keys, and for each key we have a function that returns something. And we want to create a new type with the same keys, but for each key we have the return type of the original function instead of the function itself. So we're going to need an extra type here. We're going to need return type, which is a conditional type, which we'll go in a bit later. But for now, return type just takes a function type and returns the return type. So for example, for server, since we have here string, a function that returns string, return type would just return string from this function type. So we're going to need a custom mapped type together with this return type. But first, let's understand a little bit the anatomy of a mapped type. And we're going to start by looking at record. And let's just take this record and see what it does. Now, let's remove some of these type parameters because I think they only add noise for now. And let's look at the basic anatomy of a mapped type. So we have p in, and this in is going to be either a single string literal type, or it's going to be a union of keys for our resulting type. Let's start off simple. Let's say that we have p in just name. And here we can use whatever type we want to give that property. So for example, here we could say Boolean. So now what have we created here? Well, we've created a new type that has a single property called name, and the type of that property is going to be Boolean. Now, the magic happens if instead of just a single literal type here, we have a union passed in. So for example, here we say name or age or company. Now, what's going to happen? Well, p is going to take each value in this union and is going to create a new type for which the property name is going to be whatever constituent of the union is being dealt with at the time, and the type is going to be Boolean. So here we have a record which is going to contain name, age, and company. Now, if we want to create a new type based on an existing type, we could specify here that we're not going to iterate over an arbitrary union. We're going to map over key of environment getters, for example. So what this means is that P is going to take all of the values in key of environment getters and is going to assign for each type a boolean. So we've managed to create a type with the same members as our env getter type. But now I ask you a question. What is P? Is this some magic syntax? Well, there is some magic syntax here. Map types have their own dedicated syntax. But what is P? Does it have to be named P? The answer is no. This can be any letter of the alphabet. You can choose K or P or U or T or whatever. But it is a type parameter. So basically what we're introducing here is a new type parameter. You can think of P as the variable in a for loop. So in a for loop we take each value inside of an array, for example, a for of loop. Here similarly P is going to be that variable that takes each value inside of our union of properties. So P is just a type parameter, and consequently it is just a type, and it can be used as a type anywhere that a type can be used. So for example, if we remove here boolean and we specify P, is this valid? Well, yes, P is just a type. Why wouldn't it be valid? What do we get here? Well, we get this interesting type which actually just has the keys, and each key must be typed as the same as its name. So for example, if we were to create an object here, which we're going to type with this custom record type we're creating, for port we're going to have to specify the same value port, and for server we're going to have to specify the same value server. Okay, that's interesting, maybe not particularly useful, although it could be in some cases. But what else can we do with P? Well, we can use it as a type to index into env getters. So let's do that. What do we get now? Well, we get a type that looks exactly as env getters did. Each key is typed as in the original type. Why is this? Well, P is first of all going to be server. So when typing the server key, what we're going to get here is env getters of server, which is going to resolve to this type. Then P is going to be port, and env getters of port is just going to resolve to this type, which will be the type for the port field. So this is what happened. Each property got resolved to the same type in the original type. But now that we have access to this mechanism, we can do more interesting things here, right? So instead of just preserving the exact same structure, we can start to intervene a little bit. And like I said, return type is just a type that returns the return type of a given function type. So for example, here if we pass in a function type and it returns a string, what we get in R is going to be that return type string. So if we apply this to env getters of P, what's going to happen is we get our desired type. We get server that has type string and port that has type number. So we did it. We've basically created this type without having to specify everything again, right? We've created our env type using this custom mapped type. We could even generalize this if we want. So we could call it all return types. We could say we are passing in a T and we're iterating over the keys of this type, and we're using return type for on T of P. Now the problem is that since T is just any type, T of P might not be a function, and return type requires a function. So what we could do here is we can say that this type must extend something that if it's indexable with any string, the type of that indexing operation is going to be a function that returns anything. Takes any number of parameters and returns anything. So this works, and then we can type our environment as just being all return types of and getters. And this also leads to the same result. So let's recap a little bit what we've learned about map types so far. The basic anatomy of a map type you can see here on screen. And the first part of it is this P in K, which basically means taking each P in the union K. K is usually a union that will contain valid types that represent property names, so it can be string, numbers, or unique symbols. And P will be each constituent of the union in turn. So first of all it will be name, then it will be field, then it will be whatever else is in the union. P is a new type parameter and can be used anywhere a type would be used inside the type expression U. So what is U? U is the type of the property P. So for each constituent in the union K, which is going to be name and age, and then each one of these is going to get its own type. Now you can be any type expression. It can be a constant type expression such as a string, a number, a type of env, or it can be something that depends on P. So for example, we could have just P as a type, we could have an indexing operation, and we will see later we could also have conditional types here in this expression. Remember when I said that some map types preserve structure? For example, I said that pick will preserve the structure of the type it's picking from. So for example, here if we have o.company, company is optional. Why is it optional? Well, it's optional because it was picked from the person type, whose company property is optional. So the resulting picked type will also have a property that is optional. While age isn't optional, because age was not optional in the original type. So that's pretty interesting. How does this structure preservation happen? So let's see, is the type we defined structure preserving? Now I have here a simpler example, not the generic version of the type we wrote before. And let's see if this env type is going to have the same modifiers as the type in env getters. If we add here the read-only modifier, we see that yes, indeed, our map type, the map type we wrote here, is actually structure preserving, because we were mapping over the keys of env getter, and we ended up with a new type that has the read-only modifier on the same properties as in the original type. So why does this happen? So let's see, based on what we know, how TypeScript would evaluate this type, this mapped type. Well, here inside our map type, we have in key of env getters. Well, what does this resolve to? Well, it resolves to the union of string literal type, server, or port. And if we do this, we see that things mostly work the same. Namely, we don't get errors on our indexing operations, and the type we get has the same two properties with the same types. But the surprise here is that the read-only modifier actually disappeared. So the fact that we were mapping over key of type actually turns out to be important. It's not just the fact that this map type can be composed from the parts it's made. It's not just the sum of its parts. TypeScript actually detects here the specialized pattern in which we're mapping over key of type. And it will say that, okay, since you're mapping over the keys of this given type, I'm going to preserve all the modifiers that I find in this type for each one of the properties. So this is why we end up with this read-only modifier here. Now there's actually another pattern that could be used for homomorphic map types, for these map types that preserve structure. Namely, instead of mapping over the keys of a type, we could be mapping over a type parameter which is constrained to be the keys of a given type. And again, that given type will have its modifiers preserved. And this is actually what pick does. So if you look at pick, we see that the mapping operation happens over k, where k is a type parameter that extends key of t. So it must be one of the keys of the type t. So this means since we have this pattern, we will have the preservation of modifiers that come from this type t, whatever that type happens to be. Let's see how we could play around with these modifiers. So we saw that by default, if we use key of type, then the type has its modifiers preserved. But what if we explicitly want to add modifiers? What if we want to make all properties read-only? Well, then we could just add the read-only modifier in front of this mapping expression. What if we want to make all of the properties optional? Well, we could add the question mark modifier after the mapping expression. Basically the same as we would for a regular property. Now we have a map type that produces read-only and optional properties. But what if we actually want to remove a modifier? What can we do then? And let's have a look at the function we have here. It's called getValues, and it takes an env getter, which will provide values for our environment. But let's say that some of the properties on this env getter's type are optional. And then we also want to provide some defaults, but we want to make sure that all keys have a default value. So basically, if we want to call getValues, we can specify here the getter for the port. But we don't have to specify the server because it's optional. We do, however, have to specify the default values for both port, but we will also want to make sure that server is not omitted. Right now, since modifiers are preserved, in our env type, server is optional. So how can we remove this optionality? Well, we can add this syntax. We can add minus question mark. Right? Question mark as the modifier, minus question mark removes the modifier. We could also use plus for adding the modifier, but it's not strictly necessary, just using the simple question mark also as the modifier. But to remove it, we have to use minus question mark. We could also remove read-only modifiers by using minus read-only, and this will remove the read-only modifier as well. So now we see that this server property is required in our env type, which is what we wanted. But we have another problem here, and this is not related necessarily to map types, but we have an error here when trying to map server. Why do I say when we're trying to map server? Well, the problem is that there is a property, namely this server property, which isn't just a function. It's a union of function and undefined, because that's one of the side effects of the optionality modifier, to add undefined to the type that the property originally was. How can we remove this undefined? Because we don't want it in this case. The simple answer is we have a predefined type called non-nullable, which will actually take a union and it will remove all undefined and nulls from that union. So for example, if we apply non-nullable to this type, we get back just the non-nullable parts, in this case the string signature. So we can use non-nullable on our env getters of P to remove any undefined values that may be present in our types. And now we see that we no longer have an error and the type of server is also correct. Just as a parting thought, I want to stress the syntactic nature of these homomorphic mapped types, of this behavior. Namely that we must map over key of type. It's not enough for the type we're mapping over to be some alias for key of another type. So for example, if we were to add another type, let's call it k, and this would be equal to key of m getters, and we were to use this type in our mapping, then modifiers would actually not be preserved, because env is no longer a homomorphic map type. It doesn't preserve structure because it's not mapping over key of type. So a quick recap of what we saw. We saw that some map types preserve structure, and these are called homomorphic map types, and that they are dependent on the syntax we use for mapping. If we map over key of t, that means that we preserve the modifiers of t, or if we map over a type parameter, where the type parameter is constrained to be key of t, then again the modifiers of that type are preserved. We can also manipulate modifiers. We can add the read-only modifier by specifying it in front of the mapping expression. We can remove it by using minus read-only in front of that mapping expression. We can also add the optional modifier by adding a question mark after the mapping expression, and we can remove it by using minus question mark. So let's move on to what everybody's here for, namely conditional types. Now, I know that it's a bit late into this workshop. We finally got to them, conditional types. The reason that I went through a lot of all of the other types is that conditional types are nowhere nearly half as interesting if we don't understand all of the other types that we can use in TypeScript, and all of the stuff about unions and intersections and mapped types. These are all important for us to get the full experience of conditional types. So let's have a look and let's try to see exactly what conditional types are. And for that, I want to start out with a very simple motivating question. How can we correctly type a function that returns either string or number based on the type of a passed-in parameter? So basically we have this getSampleData function, and if we pass in string, we get a string, and if we pass in number, we get a number. And there could be another option to this. We could use overloads, but let's try to solve this using conditional types. So what are conditional types? Well, in TypeScript, we can make decisions as to what the type should be based on other types. So for example, let's have a simple type, and let's say that if one extends string, then we want the type yes, otherwise we want the type no. So obviously in this case, one does not extend string. So the result is going to be no. Now if here we were to have a string literal type, then indeed one would be extending string, so the result of this would be yes. So basically when this type gets resolved, we are left with either y or n, depending on if this expression is true, if this extends expression is true. Now I want to point out that there is no other operator here. You can only use extends between types. So there's only this type of relationship that can be expressed between the type on the left hand side and the type on the right hand side. And then this condition is followed by a question mark and by the two alternates. What if the condition is true and what if the condition is false? Very similar basically to a ternary operator in JavaScript. Okay, I know what you're saying. This doesn't seem particularly useful. Okay, I always know if one extends string or if the number one extends string. What's this useful for? Well, this becomes more useful when you start to pair it with type parameters. So let's see how we can express the relationship between input type and output type using a conditional type. So let's say we have a new type. Let's say we call it return type of k. And if k extends string, then we're going to return string. If k is not the string literal type string, we're going to return number. And now if we were to instantiate this type, for example, ret of string or ret of number, we're going to see that R1 is going to be string and R2 is going to be number. So how can we use this in the function? So the first thing we actually have to do is to actually capture the value of the argument in a type parameter. So right now, if we were to say get sample data of string or get sample data of number, the type of this value parameter is always the same. It's always string or number. What we want to do is, at each call site, we want to capture whether we're passing in the type string or the type number. And as we saw this in previous examples, we can do this using a conditional type. And we can say that k extends string or number. And then this parameter will be of type k. And now TypeScript will actually capture the actual type of the argument that is passed in. So in the first case, k is going to be string, and in the second case, k is going to be number. And now that we have the actual type of the argument that's being passed in, it's no longer just string or number, we can use this in the return type. So we can say here we're returning ret of whatever k is. And now if we go to our call sites, we see that the first call is going to return a string, and the second call is going to return a number. Now, you notice here that we have an error. This is because generally when we use conditional types in generic functions, TypeScript cannot really tell how that conditional type is going to be instantiated. So it can't actually check this expression. It cannot check that this expression will actually conform to the signature of this type, of this function, that it will actually be okay. But usually what I try to do is not worry too much about the implementation. If I use conditional types, I expect to find some type assertions in the implementation of such a function, and I don't mind that. What's important is that the call site is correctly typed, because probably if you're writing a function, more people are going to call that function than are going to be writing that function, or at least hopefully that's the way it's going to be. So this is what a conditional type is. It's a way to make a decision in code based on another type. What's the anatomy of a conditional type? Well, basically the syntax is similar to the conditional operator in JavaScript. We can test any type, then we have to follow it by the extends operator, no other operator is possible, and then a potential base type, or the type we want to test, and then question mark, and we have the two branches, if true and if false. So now that we have a grasp of the basics of conditional types, let's see if we can do something more complicated with them. Let's see, how can we get the properties of a specific type from another given type? So for example, if we have the book type, we want to only get keys that have type string. So for example, in this case, name and author. So let's see how we could code this. Now I'm going to present two versions of this filtering type, because TypeScript recently added some syntax that is useful when doing this filtering. But first we're going to look at the old way of doing it, just so we get a handle of conditional types a little bit better. So let's think a little bit about what we want to do here. We want to go through all of the properties in this type, and in each case we want to decide if that particular property should stay in the result or it should not stay in the result. So let's see what this sounds like. Well, the going over each property in a type, in an object type, well, that sounds like a mapped type, doesn't it? And the second part with we want to make a decision for each property based on its type, whether it should stay in the result or not, that sounds like a conditional type. So let's start out with the first part, with going over the keys of the book type. So we can create a new map type. We can say k in key of book. And what should we say the property of type And what should we say the property k is typed as? Well, we really don't necessarily care about these types. We want to put them in the condition, but they're definitely not going to be part of the result. So let's use here k as the type for the property. And remember, we saw this type back when we introduced mapped types. And we see that this is actually a type that for each property is going to have the same type, as the name of that property. Now what can we do further here? Well, if we want to get back, for example, to just the keys of book, we could index here by key of book. Now this is obviously a very roundabout way of getting the keys, but it is a way that does produce the same result as a simple key of book. The trick is that we have control over the types of the properties here. We don't need to always specify k. So let's remove this indexing operation. And let's see what we can do here except just specify k. If books of k extend string, then indeed we preserve k. Otherwise, we return never. So what happens now? Well, for some of these properties, the type is the same as the name of the property. But for the ones that we're not interested in, the type of these properties is never. So now if we have a union of all the property value types, what we will end up is a union between never, never, name, and author. And as we saw, never is the empty set. It doesn't have any influence on a unioning operation. So what we're actually going to be left with is name and author, which is actually what we're interested in. So we can just take here key of book. So now we have this type that filtered out keys based on the type of those properties. Can we make it generic? Well, of course we can. Let's call it filter keys. Let's say they take a type T and the value type that we're interested in, and we can map over T, and we can say here if T of K extends, not string, but the value we're in, the type we're interested in, and we index here with key of T. And basically now we've converted our type to this generic form. And if we instantiate it, we can instantiate it with filter keys of book. And we're only interested in the string keys, or we're only interested in the number keys. And we can see that this first type is going to be name and author, and the second type is going to be pages and font size. Now, let's try to mess this up a little bit. What if we add an optional modifier to some of these properties? And we see here an interesting thing, namely that both pages and that those properties have actually been removed from the type. Why is that? Well, the reason they were removed is that they're no longer the types we're interested in. So for example, if we search for number strings, that number or undefined does no longer satisfy the extends clause, right? Number or undefined does not extend number. It's actually the other way around, based on how unions and sets works. And similarly for author, string or undefined does not extend string. Okay, so we understand why they were removed. So basically we don't want them in there anymore. But the question is, why do we have this or undefined now? And let's see if we remove this indexing operation exactly what the object we get looks like. And we see here that for the types that we were not interested in, we get never for the properties that are required, but we get undefined for the other ones. Why is that? Well, we would normally get never here as well, but since we also have the optional modifier, what we're left with is basically never or undefined. Never is removed, because in a union never is always removed, and we're left with just undefined. Now why do we have this optional modifier here? Because we're mapping over key of t. And as we've established, if we're mapping over key of t, then we have a homomorphic mapped type. We have a structure preserving mapped type. That preserves this optional modifier, as it is supposed to. We don't want to preserve the optional modifier here. We want to actually get never for the type of a property, not undefined. So what we can do is we can remove that optional modifier. And now we see that when this object type is created, for all properties we're not interested in, we will get never. And only for the properties we are interested in, the property type will be the same as its name. So now we can add back the indexing operation to get the values of this type. And we see that it works correctly even with these optional keys. And remember I said at the beginning that TypeScript has recently added some syntax that actually helps us to filter keys a bit easier. So what is this new syntax? Well, let's start off from our type that filters the string keys of book. And let's just remove this in the indexing part. We want to see the object we're getting. Let's just add back the removal of the optional modifier. And let's also keep both of the string keys so we have a better example. And the syntax that TypeScript has added is that inside of this mapping expression, we can actually add another clause, an as clause. Now, previously, what would happen is that we took each key in book and we mapped it to the same key in the result type. Now we can say we're mapping to maybe the same key. So for example, we can say as k, and then we get a type which maps basically in the same way. Or maybe we can specify here a constant type, and then we're mapping all of the keys to the same key. In this case it would end up as never because of our conditional type, but we can map to all keys to a single key. But we could also put a conditional type in here in the mapping expression for each key. So we could take that same expression we had before, the same conditional type, and we can say that we're mapping k to k if the key in books is of type string, or we're mapping it to never if the condition is not met. Now, what happens if we have a property that is named never in the resulting object types? Well, never can't really be a key, and it will just get removed from the resulting type. So now if we look at this type, we will see that only the string keys were preserved, right? Because we were mapping, and the keys that we were not interested in got mapped to never, and they were removed. And we don't actually care about the type of the property. We could, for example, use here any. Now if we want to get the keys, we can just say key of this. And we get back to the same name and author we were interested in. And of course we could also make this type generic. It could have the t and the value type we're interested in, and we're mapping over t again. And anything that extends the value type is going to be preserved. What's interesting is that we can actually also create a pick by type helper type. So we saw that previously we would get an object type that contained only the string keys, and if we actually preserve the type of each property by using t of k, then we could create this type which helps us pick only the properties of a specific type. So for example, we could have pick by type of book, and we want only the number keys, or we want only the string keys in our final object type. So we have R3 is going to be pages, and R4 is going to be name and author. right? If we also want to include the ones that are possibly undefined, we could specify here number or undefined, and then we get back pages and font size. But maybe this should not have this optionality removal specifier, so it does preserve the original structure of the type. Okay, so what did we see here? Well, we saw another aspect of mapped types, as well as an application of conditional types. We saw that mapped types can have an as clause, where we're going to take each key in whatever union we're mapping over, but P is not going to be the name of the property in the resulting type. It's going to be whatever the type expression C evaluates to. C can be any expression that depends on P, but C must end up being a valid type for a key, so it must be a subset of number, string, or symbol, or it can be the never type, in which case that key is going to be removed from the result. Now C is usually going to be a conditional type because that's the whole point of C, to include or exclude some keys, or it might be a string literal type, which we're going to see a little bit later. So let's look at another application of conditional types. This time we want to filter a union. And we've already seen several other options to filter unions, but now we're going to try doing it using conditional types. And the answer is that there are two predefined conditional types called extract and exclude, which can help us achieve this goal. So let's put them to the test. So let's start with a simple form of filtering. Let's see our loose Boolean type that we saw when we were filtering unions using intersections, and let's see how we could extract just the string keys using conditional types. So if we say here string loose Boolean, we can have here extract, and we want to extract just the string keys. And we see here that we're going to get just yes, no. Now if we want the number constituents of this union, we could use extract of loose Boolean and number, or we could use exclude of loose Boolean and string. And this will basically exclude all constituents that have a base type of string. So it will basically exclude yes and no, and we're going to be left with 0 and 1. And this can also be used on object types. And for example, let's say we want to extract all of the shapes that have a color member. Now we don't care what that color member is, so we could just pass any. And we see here that we're going to get the union that contains just the two shapes that have a color property. Now we could also do the same for fill, and we would get only those constituents that have a fill property. And we can also use exclude to exclude any constituents that have a fill property. Now, how does this work? Well, since basically this type is a very broad type, right? The set that it describes includes any object types that have a fill property that is of type string and have any other properties. Basically, this will work as a filter on any type that has this fill property. So let's see how this works. Let's go to definition on this type, and let's copy it in our own code so we can have a better look at it. And let's call it extract2. And let's try to use this extract2 to actually do the same thing as we did before. And it seems to work. But this is strange. Let's actually think what this type should be resolving to. So we have this type, right? And if we were to inline what exactly this type is doing, well, then we should have T is replaced with loose Boolean, U is replaced with string, and T is replaced with loose Boolean. So I hope that we can all agree that basically I just inlined extract2 right here in this version of the type. So this first type evaluates to yes and no, and this other type evaluates to never. Well, that's strange. Does this make sense? Well, does this union extend string? The answer is no, it doesn't. And even if it did, how does just yes and no make it into the result, into the resolution of this conditional type? Basically, what we've stumbled upon here is the distributive property of conditional types. Namely, that when we have a naked type parameter, TypeScript will not evaluate the conditional type as is if the type parameter is a union. So this is not what actually happens. This isn't what actually happens when TypeScript tries to evaluate our extract type. No. What actually happens is that if the condition is directly on a type parameter, i.e. a naked type parameter, and if that type parameter is a union, then the conditional type is applied to each constituent of the union. And the results are all unions to give the final type. So if we have a type C, and this is a distributive conditional type, and we instantiate that type with a union t1, t2, t3, ... tn, this would be the same as if we were to have instantiated C of t1, or C of t2, or C of t3, ... or C of tn. So, let's see. Our extract type, how does it actually evaluate? So we're evoking extract with this union, 0, 1, yes and no, and the second type parameter is string. Now we have here t extends u. The condition is over a naked type parameter. So what's going to happen is that this conditional type is going to be instantiated for each constituent of the union. So we're going to have 0 extends string, then 0 or never. If 1 extends string, then 1, otherwise never. If yes extends string, then we have yes or never, otherwise. If no extends string, then we have no, otherwise never. The first two conditionals are going to resolve to never, and the last two are going to resolve to yes and no. And this is why we end up with yes and no when we apply extract to our union. Now sometimes it is important to disable distribution because we don't always want it. And the way to do that is usually to wrap the type in a tuple. Basically, you put square brackets around the type. Now, other types would also work, but they might depend on the variance of that specific type. So it's best to stick with a tuple when you're trying to disable distribution. On the other hand, sometimes we need just the distributive behavior of the conditional type. And when we need that, we usually have a condition that is always true. So we could see something like t extends t, or t extends unknown, or t extends any, which are conditions that are true for any given t. When we see a condition such as this, it doesn't mean that the person who was writing the type didn't know what they were doing. They wanted an always true condition because they actually only cared about the distributive part of this conditional type. Now I just want to point out that this might create a surprising situation when you first encounter it. Namely that sometimes inlining a conditional type will produce different results than the actual conditional type if it's put in an alias. Like we saw for our extract example, where the conditional type produced different behavior when we used it in a type alias or when we actually inline the same behavior. While this might seem surprising at first, in my experience distribution works much like you would expect it to. It's rarely surprising, but sometimes you do need to either make sure that you disable the behavior using a tuple if you want to do something that doesn't require distribution, or you might want to actually just use a conditional type solely for the purpose of distribution. And that's what we're going to look at next. So let's look at this question. Can we, starting from a union, for example string or number, create a new union that contains an array of strings and an array of numbers as its constituents? And the answer is yes, we can do this easily using distributive conditional types. So how can we do that? Let's create a new type, let's call it makeArray, and it's going to take a type parameter t. Now, we want to create a new type that is an array of each constituent. If we just use tarray, that's going to create an array of the union type. So for example, if we create now type R and we say makeArray of string or number, we're going to end up with an array of strings or numbers. What we actually want to have is either an array of just numbers or an array of just strings. So we want to take each constituent of the union and apply this new type constructor. We want to create a new array out of each type. So since we want just the distribution behavior, we can use t extends t. We can say that if this is true, and it's always going to be true, we're going to create our new array type. Otherwise, we're going to return never. Now the false branch doesn't matter because it's always going to be true. And we see here that we actually get our strings or our number array. Now let's see what happens when we add boolean to our union. Now, because boolean is just a set of discrete values, namely true and false, we will actually see that TypeScript treats it as a union between true and false. And we will get an array of string, number, false, and true. So makeArray doesn't play well with types that are a discrete set of values that TypeScript internally represents as unions. Now, there are other types that also do this, namely enums. And if we have an enum that is A, B, or C, and we use it in our makeArray type, we're also going to see that the makeArray type will actually distribute over the union that is created by this enum type. This means that our makeArray type doesn't play well with types that are discrete set of values. But that's probably not that big a deal in application of distributed conditional type. Let's see how we can extract all the keys from a union of object types. So what I mean by all the keys is that we want to have the keys from each one of the constituents of this union. So let's see why key of doesn't really work by itself. Let's say that we have this union person and we just apply key of person. What does this get us? Well, the answer is that key of person is just going to be name. Why is that? Well, as we already saw when we try to access the properties of the union, only the common properties from all union constituents are visible. And key of respects this same idea, namely we only get the common properties from all union constituents, not the specific properties of each one of them. So how can we get around this? Well, again, we want to create a type, let's call it key of all. And we want to take each constituent of the union T. And whenever we say we want to take each constituent of the union T, then we immediately think of distributive conditional types. And we can say here T extends T, and then we want to get the keys of that particular constituent of the union. So we can just say key of T. Otherwise we don't care, it will always be never. So now if we apply key of all to person, we can see that we actually get all the keys from all constituents of our union. How did this work? Well, again, key of was applied to the first constituent of the union and we got name and field. Key of was applied to the second constituent of the union and we got name and specialty. And the union of all of these 4 items resulted in just name, field, and specialty, because the duplicated name property is just removed because it doesn't make any sense to have the same constituent twice in a union. Let's revisit the union problem that we saw at the beginning of this workshop, namely the fact that unions allow properties from any constituent of the union. We want to find a way to avoid this without using discriminated unions, which was the solution that we proposed. So here we have a union of three object types, namely doctor, engineer, and artist, and we see that they all have a common field, which is name, and they also have a specific field, namely specialty, field of activity for the engineer, and preferred medium for the artist. Now the question is, how can we ensure that these three types are not compatible with an object that contains field from another constituent of this union? And the answer is, we can actually add these fields, but we can make sure that they're always undefined if they exist. So for example, for doctor, we could add in the field, but it has to be undefined if it exists. We can also add in preferred medium, but this also has to be undefined if it exists. Now, this object literal is still compatible because at the end of the day, the object literal has to be compatible with at least one of the constituents of the union. And even though this particular object literal is no longer compatible with doctor, it's still compatible with engineer. But we can add the fields to engineer as well. But this time we want to add the fields that are not present in engineer. So in this case, we're going to use specialty and preferred medium. If these are present, they have to be undefined. Now this object literal is still compatible with one constituent of this union, namely with artist, because it can have these extra properties that are present in other constituents of the union. But if we also add this to artist, and we also make sure that we add the other fields that are from the other union constituents, namely in this case field, we see that we actually get an error on O now. We get an error that says string is not assignable to type undefined for specialty. Because, okay, TypeScript will try to see now this object literal, what constituent of the union is it compatible with? And the answer is that it's compatible with none of them. Now, if we were to leave in just one of these fields, this would work. So, for example, this object literal is compatible with engineer. This object literal is compatible with artist. And this object literal is compatible with doctor. But as soon as we add one of these extra properties, compatibility is no longer possible. So let's see if we can find an automated way to actually do all of these changes to our union constituents. But for that, let's first of all do a bit of housekeeping. Let's keep our original person union. Let's call it original person. And let's add all of these intersection types in a new union, so as we have the clean original types. So we say that this is a union with all of these extra fields, and we add them to engineer, and we add these to artist. So let's see if we can find an automated way to add these extra fields. So first, let's see what it is we're adding in each case. Let's first of all see what we're adding in the case of doctor. So if we were to create a type, and let's call it D for example, what fields are we adding here? Well, we're adding the fields that are present in other union constituents, but not in doctor. So how could we get those keys? Well, since we're adding keys from all union constituents, we could use our key of all type that we saw before. And we could say key of all original person. And now we have a union of all keys from all union constituents. And we can say that we want the keys that are not part of doctor. And we could do that using the exclude conditional type, which excludes members from a union. So we could say here that we're excluding all the keys of doctor. So now we get a union, a field, and preferred medium, which are the exact fields that we should add to doctor. And now we want to create a new type that has all of these fields, but are typed as undefined. And to do that, we could use record, which creates an object type with a set of keys, and all of those keys are typed as undefined. So we have this, but we also want to make them optional because we don't want people to have to specify them as required. So we say partial of record. And this results in the exact same type we were adding here. So can we extract this to make something generic so we can do this addition in a generic way for each one of these union constituents? Well, the answer is yes. We could call this add undefined props. We could pass as type parameters T original union and T union constituent, and we can use these in place of original person and doctor. And now if we want to create these extra types, we can intersect here with original person and doctor, and then we can intersect for engineer with a similar type, except we're going to have here engineer, and similarly for artist. Great, so now we have a type that is equivalent to what we were manually doing before, and it gives out the same errors. Okay, but this still requires us to not use our original union, but it requires us to actually go and add to each union constituent this specific type. How can we get around this? And the answer is that we could get around this using a distributive conditional type. Let's call this new type. Let's call it strict union. And we're going to have a type parameter T that is going to represent our union. Now, since we want to iterate over each constituent of this union, we're going to use a conditional type that just always evaluates to true. For example, T extends T. And then we're going to say that we're going to, for each constituent of this union, we're going to intersect T with, for now, original person, and the union constituent is going to be that T, because the conditional distributive type is going to take each member of our union, and otherwise it's going to be never. So now if we want to create our person union, we can use strict union of original person. And this has the same effect as before, namely we cannot specify these extra fields, but if only one of these fields is present, things work as expected. Okay, but this particular strict union type is still tied to this original person. Why is that? Why didn't I change this? Well, the answer is that we need the original union here. But since we're distributing over T, inside this true condition of the conditional type, T is going to be each union constituent. We don't have access to the whole thing anymore, right? We're distributing over it, so accessing the whole thing is not possible. What we can do, however, is add another type parameter, for example, T original. And we can pass in the same union twice. And now we have two type parameters, and we're distributing over the first one, but not over the second one. So while for the first union, T is going to be each constituent of original person. If we use T original and we pass in the same union, that's going to still hold as the whole union and it's not going to distribute over it. And now again we have that same type that is a strict union that doesn't allow any extra fields from other union constituents. Now, one last thing we could do, one last nicety we could do here is we could not force our user to have to pass in both T and T original, and we could actually do this using a default value for our T original type. We're just going to say that T original is the same as T if unspecified. So now we can invoke strict union with just our original person union. And actually this union itself, we might just as well inline it, and we don't need the original union anymore. So this is a way we can work around the fact that access property checks allows properties from all union constituents in our object literals. Let's look at another facet of conditional types. So let's look at this question. Let's say we have an object type that contains a series of functions that return a promise. And what we actually want to do is we want to create a new type that has the same properties, but for each function we want the resolved type of the promise. So for example, for the first one we want to have string, and for the second one we have number. So how can we do this? So we previously created this M type, which was a map type that used this return type conditional type in order to extract the return type of a function. And this works the same for this new environment type that we have here. Only we want the resolved type of the promise. We don't want promise of string, we want the string type inside that promise. So the first question we need to ask ourselves is, okay, how does return type work? What does it do? And we can actually see its definition, and let's just bring it here so we have it right in front of us. We can remove the type constraint, that's not that interesting for us right now. But what this type says here is, if T extends something that is a function that has any arguments and returns anything, then give me that anything. This is what that infer keyword does there. It introduces a new type parameter, and basically that location acts as a wildcard. Anything could be there. But if the rest of the type matches, then whatever is at that type location will be put in the type parameter R. And so we can use this new type parameter R on the true branch of the conditional type. We can't actually use it on the false branch because since it wasn't actually inferred, there's nothing in it, so it doesn't make sense to actually have access to it ever on the false branch. But on the true branch, we get whatever was at that type location. Now I want to stress that you can use infer new type parameter anywhere where a type expression would be expected. So for example, here you could have an object type and you could use infer in the position of a property type, or you could use it in a generic type argument, or you could use it basically anywhere. So if we want to actually get the type inside of the promise, well, we could use the same infer keyword. And we could say that if T extends something that is a function which has any arguments, and it returns a promise, and that promise has a type argument that can be anything, give me whatever is at that location, whatever is the type with which the promise was instantiated with. So now let's call this resolved return type. And if we use this type here, we can see that we can actually get the promise resolved type, right? We can get here string or we get number. So this was a very simple way to resolve our problem. So what is the anatomy of such a conditional type? Well, we have again T extends, and then we have a type expression which can contain any number of inference points, places inside the type where we don't actually have a specific type we want to match, but we want to extract the type at that location. And this can be any number of type parameters that we introduce. And then on the true branch, we have access to these new type parameters and we can use them. On the false branch, we can't use them because they weren't actually inferred. So now we know that conditional types have three behaviors that we may care about. They have their actual conditional behavior, where we can make decisions based on the type that is used in the condition. We can have their distributive behavior, where we can distribute over the constituents of a union. And we can have their inference behavior, where we use these conditional types to extract parts of other types, like we saw with the promise and the return type of a function. Now, which one of these three behaviors you want really depends, and sometimes you may use all three of them, as we will see in a future example. But definitely you need to keep in mind that these are three separate behaviors, and you can use any one of these three depending on your needs at any specific moment in time. So let's look at another type that we might want to create. In this case, we want to create a type that applies the read-only modifier to all levels of a type. So for example, if we have this particular type, which has several properties and several nested properties and also an array, we want to make sure that the read-only modifier is applied at every level of this type. So how can we do this? We can do this with a mapped type. Now, first of all, I want to prove that the original read-only mapped type doesn't actually work in this case, because that will only apply the read-only modifier to the first level of our type. So we'll only get read-only modifiers on REST API and DB servers. We won't get them on these inner properties. So how can we achieve this? Well, let's start with our read-only mapped type. Let's change its name to deep read-only. And for now, it has the same behavior as the read-only type. But what we can do now is we can actually take this type and call it for each nested property that we have. So the type for each key won't be the same as the type in the original type. It will be a deep read-only version of it. And let's see how well this works right out of the box. So we can see that the read-only modifier is applied on the first level, and it is also invoked for the nested types. However, it's a little bit difficult to read exactly what this is doing. Now, there's a trick to actually getting TypeScript to expand out all these deep read-only types. Namely, if we add an intersection with an empty object type, we actually get a better picture of the finally resolved type. So we see here now that we have read-only on the first level of REST API. We also have read-only on the nested properties of this object type. And we also see that for the array type, TypeScript created a read-only array that in turn has items that have the read-only modifier applied to each one of these items. Now I want to point out that in the past this type actually used to be a lot harder to write, and you might find versions that have all sorts of special conditions for example, array, or for object, or for other various types, or for primitives. But in recent TypeScript iterations, several things have changed. Namely, for example, the fact that mapped types actually get applied now to items inside an array. For example, here we see that it was applied directly to the item inside the array. And also, if we apply a mapped type to a primitive, it actually won't change that primitive. So these are all improvements that were made and which make this type a lot easier to write. Now there is one case that it doesn't handle it correctly. Let's say we have a function let's call it time, which is a function that returns an object, and let's say this object has day and, I don't know, time. Now, if we apply our deep read-only type to this, we will see that the time property actually ends up being an empty object. Why is this? Well, it's because TypeScript doesn't really handle mapping over a function all that well. And indeed, in this case, it's not exactly clear what it should do. Because a function may have parameter types, it will have return types. It's not clear what to apply the mapped type to. But for our purposes here, we would like to apply the deep read-only modifier to the return type. So what we could do here is we could say if t of p extends a function with some parameters, we want to infer those parameters, and we also want to infer the return type. Now what we're going to do is we're going to create a new function which has those same parameters, but it has a deep read-only version of our return type. And otherwise we apply the deep read-only type just as before. So let's see how this looks now. We see that our time function has now a better type. It is a function, at least that was preserved, which has a return type that is read-only. Now if we were to add some parameters here, we would see that those are preserved as expected in the mapped type. So deep read-only, we can write it pretty easily these days, but there might still be special cases that we need to consider in order for this to work as expected. So for example, if we have start time and this is a date, well, date is an object type, so it will get sort of mangled in all sorts of ways. Maybe for date, we don't want to actually apply the read-only modifier, we want to leave it as date. So in that case, we might also want to add here, if t of p extends date, we want to just preserve date. We don't want to actually transform this with any sort of modifiers. And now start date will actually just be a regular date. It won't be put through this read-only map type. So we're going to move on to the final type of type constructor we're going to see in this workshop, namely template literal types. Now the motivating question for introducing these types is going to be, given an existing type, can we create a new type that has methods that have the same name as the properties in the original type, but prefixed with get or set? So for example, here we want to transform our env type into a similar type, but each key has been prefixed with a get. So how can we do this? So let's think a little bit about how we could get something similar in JavaScript to this. So if we already defined a constant, let's call it is an admin, and we wanted to create a new constant that is get is admin. Well, we could use template literal types to do this. We could prefix a get here, and then we could interpolate is admin. Now the funny thing is that TypeScript actually supports basically the exact same thing in typeland. So if we remove the const here and we replace it with type, this basically works pretty much the same. Namely, isAdmin is going to be a string literal type, and getIsAdmin is actually going to be a new type that has this get prefix, and then it has interpolated inside it this isAdmin literal type. So how can we transform this type to the other type then? Well, the answer is using a mapped type, of course. So we can use p in key of env, so we're mapping over env. The type of each property is going to be a function that returns env of p. And now we're going to use the as clause we saw in our previous examples. And we can say here we're mapping p as a string literal type that has get and then has whatever string literal type is contained by p. And let's see if this worked. The answer is yes, it did exactly what we expected it to do. Now there's only one small problem, namely is admin and is server should really be capitalized inside of these property names. Fortunately, TypeScript provides a type that helps us do exactly this, namely the capitalized type. And now our type is exactly what we would like it to be. So this was a pretty simple way to actually do string manipulations and to create a new type based on an existing one and to map the property keys to something else. Now if we also wanted to have set methods, we could use an intersection and we could do basically the same thing only for set functions. And we could say that the function here takes a value that is of type p of env and it returns void. So now we have a full type that has both get and set functions. Now you may be wondering what exactly is the definition of capitalize. I mean, so many other types we saw had a more elaborate definition when we actually look at them, and we could have learned a lot from them. Capitalize is an exception to this. It is actually what is called an intrinsic compiler type, namely that this type has a special meaning to the compiler and it will perform this conversion of string literal types from their lowercase version to their capitalized version. There are several other intrinsic types. Namely, we already saw capitalize, there's uncapitalized, which does the opposite. There's uppercase, lowercase, and that's about it. Let's look at a more complicated transformation we might want to do. Let's say we have an env type which contains properties that are prefixed with x underscore, and then they use underscore to separate the components of each name. We want to transform this into something that is more JavaScript oriented. So we want to remove that underscore and we want to transform it to the casing that is usually found in JavaScript. So let's look at the first part of this problem. How can we remove this x underscore prefix that we find in front of each property? Now the first question we have to ask ourselves is how would we add this x prefix? And here we created a small helper type that accepts any string literal type as its parameter and returns x underscore and then followed by that type parameter. So if we were to invoke this type with, for example, is admin, what would happen is that we would get this x underscore is admin. Okay, so this is how we add it, but how do we remove it? And the answer is that we can remove it using a conditional type. So let's say we accept any p that extends string, any property name. Now we can ask the question, does p extend add prefix? If so, infer what parameter it would be invoked with. So how does this logic happen? Well, if p extends something that has an x underscore in front of it, then this condition is going to be true. And what this inference size is going to give us is actually what comes after that x underscore. So for example, if we create a new type r and we say it's remove prefix of let's use this. Then we see we've managed here to extract just the isAdmin part. Okay, so now we know how to remove the prefix. The question is, how can we transform this type, isAdmin, to isAdmin starting with a lowercase? So for that, we're going to have to split our string types using this underscore. And how could we do that? Well, again, using conditional types. So let's say we want to create a new type. And we're going to call it convert to camel case. And we're going to say here, if t extends a template literal type that has some sort of prefix, then is followed by an underscore, and then we want to infer whatever comes next, we're going to return a lowercase version of the head or never. And we're also going to want to add the tail part. But for now, we're just going to add it as the original tail without transforming it in any way. So let's see what applying this to isAdmin will achieve. So we see here now that we've removed that first underscore, and we have the admin after the initial is token. We could just capitalize this as well. We'd also have to lowercase it. But this wouldn't really deal well with property names that have multiple tokens. So if we do it like this, then we still get those underscores. So how can we remove underscores? Well, we're going to have to use a recursive conditional type. So basically, we're going to remove one underscore token, and then we're going to recursively call remove underscores for the rest of our string until it is no longer a string that contains underscores. So we can say here that if t extends, again, something that has a head and a tail and contains an underscore in between, we're going to keep the head, but we're going to capitalize and lowercase it. And then after it, we're going to put whatever remove underscores returns for the tail. If the type did not contain an underscore, well, we should still capitalize and lowercase it. And let's just add some constraints here. These should all extend string. So let's see what calling remove underscores on the tail in our camel case type will do. We see that we get the exact type we want. Basically, we managed to remove the underscores successively from all of the positions it was present in our property name. Now, putting this all together is just a simple case of using our new convert to camel case type in a mapped type. So mdata could become p in key of env, and we're going to map using convert to camel case, And we're also going to remove prefix from our property P. And we're going to say that the property type is env of P. We're preserving the same property type. So now env data is going to be is admin and max requests per minute, and everything seems to work as expected, except for the X server, which doesn't contain an extra underscore. What we forgot to actually do here is if the initial type does not contain an underscore, we should lowercase it. So now it all works as expected. The ability to do string manipulations in the type system was something that has been requested for quite a while, and personally I'm very happy to see it's finally made its way into TypeScript. It's a great feature, and as we saw, it has great potential and unlocks a lot of new type transformations that we can do that previously were not possible. So the final type we're going to look at today is a type that helps us convert a union to an intersection. And this is going to tie in some of the distributive and the inference behaviors of conditional types that we've previously seen. So the first thing we need to look at in order to be able to build this type is we need to look at unions of function types and with what they are actually invocable. And for example, let's take the union we have that we're trying to transform, and let's create a new function union. And we're just going to write out this type. And let's say these functions take different parameters and return void. Okay, and let's declare a variable that is of this type. Let's say it's a function and it has the type function union. And let's assign to it randomly either a function that deals with something that has type foo of type number, and console logs this, or it's something that has a bar property and it logs out that bar property. Now the question is, what is it safe to invoke this function with? Now the TypeScript compiler here tells us that what it's safe to invoke this function with is an intersection of the two possible parameter types. So even though we started out with a union of functions, the parameter that we can pass into this union of functions is actually going to be an intersection of all possible parameter types. Now why is this? Well, given the fact that we don't know which function it is, it could either be the function that accesses foo or the function that accesses bar. There is only one possible safe solution, is to pass in a parameter that satisfies all possible implementations of this function. So we need to pass in something that has both foo and bar. So this is why if we have a union of functions, we need to pass in something that is broad enough to satisfy all possible implementations that could be passed into this function. Now for object types, this intersection will result into a type that has more properties. Unfortunately, if we were dealing here with primitive types, the intersection would probably reduce to never. Because if you have, for example, string, one parameter is string and the other parameter is number, the intersection would produce never, and is basically a function that cannot be invoked because you cannot have a value that is both a string and a number. There's no parameter that could work to satisfy all possible implementations of this function. So what does this have to do with our union to intersection transformation? Well, if we were to use a conditional type on this union of functions, what we would get is the parameter that would be valid to invoke this union of functions. And let's try this. Let's say we have a type R, and we want to take our function union, and if it extends a function which has a parameter and returns, let's say, void, then give us that parameter type. And indeed here, if we look, we can see that this R type is going to be the intersection of these two parameter types. So starting from a union of functions, we were able to get an intersection of the parameter types. Okay, but I hear you say, I don't have a union of function types. I have a regular union. I want to get the intersection. Yes, but building a type that transforms a union of whatever into a union of function types that has each constituent as a parameter shouldn't be that difficult given what we know so far. So let's say we want to generalize this function union with a type parameter t that is going to be the union. And we want to take each constituent of this union. So basically we're going to need a distributive conditional type because we want to operate on each constituent of this union. So we're just going to use a true condition. And we're going to create a new function type for each constituent where the parameter to this function is going to be the union of the constituent of the union. Otherwise, we're just going to say never because the condition is always true anyway. So now we can use this function union type to transform any given union to a union of functions where the original constituents of the union are set as the types of the parameters. So if we put this together, we can actually create our union to intersection type now. What would it look like? Union to intersection of t. First, we want to transform the union to a union of functions. And then we want to say that we want to extract from this union of functions whatever parameter we can use to invoke this union of functions. So what will happen here, as we saw, is that given that we have this union of functions, what is going to be invocable with is the intersection of all parameter types, which, as we saw, we mapped each constituent to one of these parameter types. So now if we use our new union to intersection type on our original union, we see that we get the intersection that we want. Now, you might have seen this type on the internet without this extra helper type, and indeed it's not strictly necessary. We could just inline it right here, and we would get the same type, if slightly harder to read. So we've made it to the end of this workshop. Thank you very much for listening. If you have any questions, at me on Twitter. I'm going to try to answer as many questions as I possibly can. If you've made it this far, I think that you're probably on pretty good ground to tackle any TypeScript problem you will find in the future. So thank you for listening and have a nice day.